So for this section, we're going to be looking at the comparison test. And it's actually a fairly simple concept to understand, but it takes a little bit of tiny bit of cleverness to figure out how to use it. So let's talk about it, huh? I'll talk about it because it's a video. So this is the first part of the comparison test. Let me explain. We're going to assume that we have two sequences. Remember, a sequence is just a formula for a set of numbers. Actually, it's just a set of numbers, but the way I'm describing it here is A sub n is a formula for a sequence. B sub n is a different formula for a sequence. If I put the summation on it, the summation on it, then it becomes a series. And a series is when you're adding things together. So, what redo? Okay. I'm saying assume that I have some sequence that's actually two sequences that are bigger than 0. That's what I'm saying here. And A sub n is the small one, B sub n is the big one. Now, what do I mean by that? Well, if I plugged in an n value, any n value greater than some number, what I'm trying to say is, okay, so let's suppose, I'm going to erase this in a little bit. Right now I'm trying to explain what it means for A sub n to be smaller than B sub n after some n value greater than some number. So suppose A sub n is going to be red, B sub n is going to be blue. So I mean, A sub n could do anything that it wants at the very beginning. But after some n value, after some number, I want, let's just say that. I want, well, okay, that's fine. And then I could have some series B, or sequence B, where after some value, B is the top function. That's what I mean by being bigger. So this is definitely above this. So even though it does whatever it wants to at the very beginning, eventually, this is what this part means. It means eventually. So for all n values greater than some number, that just means eventually. I'm going to put that in green. And for series, we actually don't care what happens when n values are relatively small. We care about it when n values are approaching infinity. So assume that we have two sequences where this one is the top series, sequence, and this one is the bottom sequence. Something like this, where eventually B, like on a graph, B sub n, we can think of it like a function. I mean, of course it's not a function, but we can think of it as a function where B sub n is the higher function. It's the function that's closer to the top of the graph than A sub n. Okay, hopefully that makes sense. So, assume that we have A sub n, which is smaller than B sub n. And this is the way I remember it. B sub n is bigger. A sub n is like anti-bigger. No. B for bigger. If this sequence, if this series, because I put the summation in there, if this series converges, if the bigger series converges, maybe I'll write that in green. So if the bigger series converges, then the smaller series has to converge. So that's the first part. If B sub n converges, then A sub n also converges. If the bigger series converges, then the smaller one has to. Whoops, I cut myself off. Has to. Then the smaller one has to. Now let's go back to our picture. We said that, well, let's make a graph. When we're saying that eventually A sub n, so does whatever, and then, actually, let's draw the bigger one first. Suppose we have the bigger one, and it converges to some value here. So we're saying it converges. That series converges. Now we're thinking about the series. I guess it wouldn't have that part, but it doesn't matter. Suppose this one converges to this value. Converges, so like the limit of the partial sums goes to some number. Okay, great. And I know that this one, no matter what it does, has to be below this. That's what I'm assuming here. I know that it has to be below. So no matter what it does, it cannot go past that. So it has to converge also. I mean, I guess it could diverge this way, but we already said that it has to be greater than 0. So actually it can't do that part. It can't do that. So hopefully that makes sense. This one, the bigger series, bounds the smaller series. Hopefully that makes sense to you. That's what this first thing is saying. If the bigger one converges, the smaller one is bounded by the bigger one, so it also has to converge. And it works the other way for divergent series. So there we go. If the smaller series diverges, then the bigger series also must diverge. And I'm going to draw a similar picture to provide an argument for that. Again, we have, now I'll first start out by drawing the smaller series, which will be red, because we said it was the smaller one. So we're saying it does whatever it wants, but I know that eventually it diverges, and it just goes up and up and up and up and up. Well, if I already know that b sub n is bigger, it's like, okay, well, it's like the red one is pushing the blue one to also diverge. Because if the smaller one diverges, and I know that there's a bigger one for every n value after that, then, well, the bigger one has to diverge as well. It's like it's pushing it upwards. That's how I think of it, at least. Hopefully that makes sense. We'll get to some examples later on. But the key part of this is understanding, of course, these two things. And then you'll be given either an a sub n, and you'll have to figure out a b sub n, or you'll be given a b sub n, and you have to figure out an a sub n. And you actually have to figure out which one you're given. So that's the hard part, but I think it's very, very satisfying when you understand it and you actually start doing problems well.